Hey, welcome back. In this video, we're going to continue discussing partitions, and we're going to also look more at generating functions. In particular, we're going to apply generating functions to help us count partitions. In the last video, we defined partitions, we saw a real-world application of them in biology, and we looked at some ways to count them besides generating functions. So we looked at counting them using bijections and using Fair diagrams. We used both of those methods to show that the sizes of different sets of partitions were the same. Just to review, a partition of n is just a non-increasing sequence of positive integers that sum to n. And we saw some examples of partitions. So we saw when n equals 5, we got 7 total partitions. So those are all 7 partitions of n equals 5. And we defined this function, p of n, to be the number of partitions of n. So from the list that we drew for n equals 5, we know immediately that p of 5 equals 7, assuming that we didn't miss any partitions. And another one that I mentioned in the last video is p of 0. P of 0 equals 1. This is because there's exactly one way to write 0 as a sum of positive integers. You just write it as the empty sum, where there are no positive integers, and that's the only way. So p of 0 is 1. And what we want to do in this video is find a generating function for p of n. So we want to find a way to calculate this polynomial, I equals 0 to infinity, of p of I times x to the I. And we're going to break it down into some simpler polynomials and represent this one as a product. And we need to see how to do that. And so I will clear this so we can look at the bullets on this slide. So like I said, we're going to count the partitions of n using generating functions. And in order to get the main generating function, the one I wrote at the bottom that I erased, n equals 0 to infinity of p of n times x to the n. In order to get that one, we're going to first define some simpler polynomials, and then we'll represent that one as a product of the simpler ones. The simpler polynomials will be of this form, pi of x, and that's going to be for each positive integer I. And in order to build pi of x, we're going to allow pi of x to count the number of ways that we can represent each integer just as a sum of i's. So pi of x will only use i's in the sum, and pi of x will be defined for each positive integer I. So each possible positive integer that we can have in a partition will occur in some pi. But pi will be much simpler to compute than the partition function for p of n, because for pi, we only have to worry about multiples of I. So let's consider an example. To calculate pi for I equals 2, let's say. If we want pi of x, so p2 of x, each power of x, so have x to the 0, x to the 1, x to the 2, and so on. So each power of x, we want the coefficient of that power to be the number of ways that we can write that power as a sum of i's. So 0, that's our first power. How many ways can we write 0 as a sum of i's, where I equals 2? So we want to write 0 as a sum of 2's. We can just write it as the empty sum, so we get a 1 in front of the 0. Next power is 1. How many ways to write 1 as a sum of i's when I equals 2? Since 1 is odd and I is even, 2 is even, there's no way to write 1 as a sum of 2's. So we get a 0 in front of the x to the 1. X to the 2, for x to the 2, our power there is 2. We want the number of ways to write x to the 2, or to write 2 as a sum of 2's. And there's only one way. We can just write 2 as a single 2. So we have a 1 in front. Now we can look at the x to the 3. How many ways to write 3 as a sum of 2's? And there's no way, because 3 is odd, so 0 in front of that. And then 4 is our next power. 4 we can write as a sum of 2 2's, and that's the only way. So we have a 1 in front, and we have a 0 in front of the x to the 5th, and so on. So pi of x in general, we're going to get a coefficient of 1 in front of the powers of x, where the power is a multiple of I, and we'll get a coefficient of 0 in front of all the others, because any powers that are not multiples of I cannot be written as sums of i's. So the only powers that can be written as sums of i's are just the multiples of I. And that means that pi of x is just 1 times x to the 0 plus 1 times x to the I plus 1 times x to the 2i, and so on. So it just has 1 in front of each power of x where the power is a multiple of I, and 0 is in front of all the others. And we can write this sum in a simpler way as the sum from j equals 0 to infinity of x to the ij. And we can see that that sum can actually be simplified. And we will assume that the absolute value of x is less than 1. It's not important that this sum converges, but just to have it converge, we'll assume the absolute value of x is less than 1. So all that matters here using generating functions is the polynomial arithmetic. The convergence really doesn't matter, but I'm just choosing x so that it does converge. And if the absolute value of x is less than 1, that also means that the absolute value of x to the I is less than 1. And so this sum right here is a sum x to the 0 plus x to the I plus x to the 2i, and so on. Same thing we saw over here. And we saw in the video where we did summations of infinite geometric series. So when we proved the formula for that, we found that the formula was equal to 1, since our first term here is 1, it's x to the 0, divided by 1 minus the common ratio, and that's x to the I. And I'll just note another way we can write this sum here, which might make this more clear if there's any confusion. We can write this as x to the I to the 0 plus x to the I to the 1 plus x to the I squared, and so on. So same thing, but maybe seeing it from that's a little clearer. Now, we have this as our value of pi of x for each positive integer I. And in order to get the partition generating function that we're looking for up here, all we have to do is multiply together the polynomials for each I. And that's because we can use any positive integers in the sum for a partition. So we have to include all the PIs because any possible I can be used in the partition. And let me erase a little so we can see the next bullet. So specifically, if we're trying to find P of n, we can just find the x to the n coefficient of the product of the polynomials, P1 of x, P2 of x, P3 of x, and so on. So we can write that sum I have at the top. Sum n equals 0 to infinity of P of n times x to the n. We can write this as the product I equals 1 to infinity of Pi of x. And this is each Pi of x. So you can write it out like this, or you can write it in the more compact form like that. And this is what I wrote here. So I wrote it slightly different on this bullet, because as you can see, product I equals 1 to infinity of 1 over 1 minus x to the I is the same as product I equals 1 to infinity of Pi of x, because Pi of x is equal to 1 over 1 minus x to the I. Again, we're assuming absolute value of x is less than 1. Not that it's that important for this to converge. All that's important is the polynomial arithmetic, because we only care about the coefficients. So this gives us a pretty simple way to calculate P of n for any n, just using finitely many terms in the product. So we don't have to use the full infinite product. We can just do the product up to the n that we're trying to get. So if we're trying to get P of 7, let's say, we want the coefficient of x to the 7th in that product. But then we notice that for I equals 8, I equals 9, all the I values higher than 7, their polynomials are going to have a 1 times x to the 0 plus 1 times x to the I plus 1 times x to the 2i. If I is greater than 7, the 1 times x to the I, the 1 times x to the 2i, all the multiples of I besides the 1 times x to the 0, they're not going to affect the coefficient of x to the 7th. So none of the I values higher than 7 are going to have any effect on that coefficient. So we can terminate the product at I equals 7. We only have to go up to 7. And now we see we still have some infinite stuff here. So we have a 1 over 1 minus x to the I. And that we know is equal to 1 plus x to the I plus x to the 2i, going on forever. So the powers and multiples of I. But the thing about that is we don't have to write out that whole infinite polynomial either. So we can terminate that one as well. We can terminate it at the highest power of x that is less than or equal to x to the 7th. And that's what I do in the next bullet. So each of those terms, I equals 1 to 7, so we have a total of 7 terms in the product. And each of those polynomials, I terminate them at or less than x to the 7th. So our first one, I equals 1. We have 1 plus x squared plus x cubed plus x to the 4th, all the way up to x to the 7th. So I terminated at x to the 7th. And that's why I terminated the P1 of x. So I terminated it at the x to the 7th. For P2 of x, we have 1 plus x squared plus x to the 4th plus x to the 6th. And then the next term would be greater than x to the 7th. It would be an x to the 8th. So we terminated at x to the 6th. P3 of x, we terminate it at x to the 6th as well. We get 1 plus x cubed plus x 6th. The next one would be x to the 9th, which is too large, so we terminate it at x to the 6th. For P4 of x, we just terminate it at x to the 4th, because 1 plus x to the 4th, the next one would be x to the 8th, which would be too large. Same with P5 of x, we just terminate it at x to the 5th, because x to the 10th would be too large. P6 of x, we terminate at x to the 6th, because the next one would be x to the 12th. and p7 of x terminate at x to the 7th clearly because the next one would be x to the 14th. And so we just multiply together these 7 finite polynomials. And you can just take this and you can put it either in your calculator or Wolfram Alpha. You can write a script in Python and do it if you want. And then you just have to check the coefficient of x to the 7th. And you get a 15x to the 7th when you expand this out. So if you write expand that and expands it out, you get 15x to the 7th. So the answer, final answer, is 15. So P of 7 equals 15. So this is a pretty simple way to calculate P of n for any n, as long as n is some pretty small finite number. And even if n is not that small, you can easily write a computer program to do this. And it'll be much simpler than just trying to brute force calculate all the partitions. So we can use these partition generating functions. In addition to calculating the function P of n, we can use them to find other sizes of sets of partitions. So other special classes of partitions, we can count their size as well using generating functions. Let's see an example. So we'll define a subset of the set of partitions of n, and this subset will be the partitions that have no ones in the sum. So we can consider 5 again, n equals 5. And we can write that as 1 plus 1 plus 1 plus 1 plus 1, 2 plus 1 plus 1 plus 1, 3 plus 1 plus 1, 4 plus 1, and we got 3 plus 2, and we had 2 plus 2 plus 1, and we have 5. So that is n equals 5. Let me write that 5 a little clearer. And the number of partitions with no ones in the sum. So this one has no ones, and this one also has no ones. Let's also look at this for n equals 4. So n equals 4. We have 1 plus 1 plus 1 plus 1. We have 2 plus 1 plus 1. We have 3 plus 1. We have 2 plus 2. And we have 4. And the only ones with no ones in the sum are 2 plus 2 and 4. So we got 2 for both of those. It's interesting. And another way to say this is that f of n is the number of partitions where none of the parts are equal to 1. And in order to count f of n, we're going to use partition generating functions. So we're going to consider the same generating function we had on the last slide. So that was that product I equals 1 to infinity of pi of x. But we want no ones. So we want to remove p1 of x from that product. So p1 of x is giving us the ones in the partitions. So if we don't want any ones, we can just remove p1 of x from the product, which gives us the product I equals 2 to infinity of pi of x. So that's all we have to do. To remove the ones, we just take p1 of x out of that product. And that will be our generating function for f of n. So we'll define this polynomial f of x, which equals the sum n equals 1 to infinity of f of n times x to the n, And this is how we can calculate that generating function. It's just going to be the same product we had on the last slide without the first term, without the I equals 1 term. So product I equals 2 to infinity of pi of x. And another way to write that is just product I equals 2 to infinity of 1 over 1 minus x to the I. Because again, as we saw, pi of x equals 1 over 1 minus x to the I. I'll just note again, absolute value of x less than 1 to get the sums to converge. And we can see from here now that f of x times p1 of x equals p of x, big P, where big P of x is our standard partition generating function. So big P of x is the sum n equals 0 to infinity. Oh, and this should say a 0 right here. So that's a typo right there. That should definitely say 0. So that's not a 1, that's a 0. So P of x is the sum n equals 0 to infinity of P of n times x to the n, which we saw is the same product right here. Product I equals 1 to infinity of pi of x. So f of x right here is the product I equals 2 to infinity of pi of x. P of x right here is the product I equals 1 to infinity of pi of x. So we see that P of x is just equal to P1 of x times f of x. So the only difference between P and f is that P has this extra P1 of x term. So we can say P of x equals P1 of x times f of x. And we know what P1 of x is. We know P1 of x equals 1 over 1 minus x to the 1. All I'm using is this right here. And that means that f of x over 1 minus x equals P of x. So we can say that f of x equals P of x times 1 minus x. Just multiplying both sides by 1 minus x. And so we can write that, and this summation actually starts at the right n value, so that's good. So it starts n equals 0 to infinity of f of n times x to the n. So this equals 1 minus x times the sum n equals 0 to infinity of p of n times x to the n. Why is that? Well, all we did is we took f of x. F of x is equal to the sum n equals 0 to infinity of f of n times x to the n. So we just substituted. For this left side, we substituted what it's equal to in this equality here. Now, the right side, we had a 1 minus x. That's how we got this 1 minus x right there. And then we had a p of x. The p of x right here, again, is defined as the sum n equals 0 to infinity of p of n times x to the n. So we just substitute that sum in right here. And now we can simplify it a little bit. So we have a 1 minus x times the sum n equals 0 to infinity of p of n times x to the n. So we can use the distributive property on that 1 minus x, and we get the sum n equals 0 to infinity of p of n times x to the n. That's from the 1. So the 1 times the sum gave us just the sum. And then we have minus x times the sum. So we get minus the sum from n equals 0 to infinity. So same bounds on the sum of p of n, but we have this extra factor of x. So that increases our power of x from n to n plus 1. Now we can simplify even more. So the left side is still the same. On the left, we still have sum n equals 0 to infinity of p of n times x to the n. But now, this sum right here, instead of starting it from 0, we can start it from 1 and just shift the n's down 1. So n starts at 1 instead of 0, and we just make each of the n's here an n minus 1. So the n became an n minus 1. The n plus 1 became an n because it's an n minus 1 plus 1. And now we can see that this difference of sums that we have here, it's easy to write it just as p0 times x to the 0. So p of 0 times x to the 0. that's from this sum. So that's the term in this sum that's not in this sum. So that's the n equals 0 term. So this is the only n equals 0 term. N equals 0 from this sum, and there's no n equals 0 from that sum. Now this sum over here, all the terms in it come from both sums. So both sums contribute to this one. That's why I have two arrows going to that one. And we go from n equals 1 to infinity, because n equals 0 is only in the left sum. N equals 1 is in both sums. And we have p of n minus p of n minus 1, and that times x to the n. So we use the distributive property again there, but in reverse. And this, again, is just the sum n equals 0 to infinity of f of n times x to the n. So we see f of 0 equals p of 0, which makes sense. The number of partitions of 0 with no 1s, the empty partition, that one works, and that's the only one. And that's the same as the number of partitions of 0. It's just 1, so 1 for both of them. And we see, more generally, when n is greater than 0, we can write f of n equals p of n minus p of n minus 1. And I'll erase a little so we can actually see that. So there we go. There it is. So we started with the sum n equals 0 to infinity of f of n times x to the n. And the f of 0, x to the 0 part was just p of 0 times x to the 0. So the sum n equals 1 to infinity of f of n, x to the n, this is just this sum on the right. Sum n equals 1 to infinity of p of n minus p of n minus 1 times x to the n. And so we get that the f of n has to equal the p of n minus 1 for each n. So for all n that are greater than 0, strictly greater than 0, so not including 0, because we haven't defined p of minus 1, so it wouldn't make sense to say that for 0. I'll mention one more thing. So there is a reason why we looked at n equals 5 and n equals 4 up here. So we see f of 5, we calculated it up there. We saw that f of 5, f is the number of partitions with no parts equal to 1. We only found 2 of them. So this was 2. And this also equals p of 5 minus p of 4, because we get 7 minus 5. So for 4, we found a total of 5 partitions. 1, 2, 3, 4, 5. So 7 minus 5 also gives us 2. So for that example, we see that this formula that we just derived is true. And it should be true because we proved it's true using the generating functions. But there's an example of it. Okay. So we can consider a slightly more complicated problem involving generating functions and partitions. So here's the claim. I claim that the number of partitions of n in which every part is distinct. So in other words, every term in the sum is a different number. There's no number that occurs more than once in the sum. And I claim that the number of partitions of n in which every part is distinct is equal to the number of partitions of n in which every part is odd. In other words, every term in the sum is odd. So let's look at the example of 5 again here, just to see n equals 5. So we have our partitions again, only 7 of them. Okay, so we got 7 total partitions there. Now we want to look at the ones where every part is distinct. So every part is distinct. This one right here it has a part repeated 5 times, so definitely not every part distinct. This one has a part repeated 3 times. That's bad. So I think I'll note this with X's on the left for not having the distinct parts. So all 3 of these are bad. They have repeated parts. This one's good. Distinct parts. 4 and 1 are the only parts, and they only occur once. 3 and 2 only occur once here. That's good. 5 only occurs once here. That's good. And 2 plus 2 plus 1, repeated parts. It's bad. Now we can, on the right side, we can check partitions of n in which every part is odd. Are all the parts odd? Yeah, so here all the parts are odd. They're all 1. Here, no, we have a 2 there. So we have an even part, so that's bad. All the parts are odd here because we just have 3s and 1s. Here we have a 4, that's even, so that's bad. Here we have a 2, so we have a non-odd part, so this is bad. 2 plus 2 plus 1, we have 2 even parts, it's even worse. Here we have only a single part and it's odd, so this is good. Now we can count each side. Hopefully I marked this correctly. So the number of partitions we found of 5 in which every part is distinct, it looks like we only found 1, 2, 3 of them. So for n equals 5, we got 3 on one side. And then let's see, so 3 was the left. So I see 3 checks on the left. Check here, 1, 2, and 3. Now we count the right checks. 1 right check, 2, and 3. So we got 3 on both sides. So the statement is true, and we're going to prove it's true. And this example is just to illustrate what it's saying for clarity. So we're going to define this function Q of n, and it will be the number of partitions of n in which every part is distinct. And so we want to look at how to calculate the generating function n equals 0 to infinity of Q of n times x to the n. So what we can do is we can start with the standard generating function. So we can start with this product, I equals 1 to infinity of pi of x. And we can look at how should we modify this to get our generating function for q. So let's recall, what is this polynomial doing here? So we have product I equals 1 to infinity. And then we can write these polynomials out in their infinite form. So we'll write them as 1 plus x to the I plus x to the 2i plus x to the 3i plus x to the 4i, and so on. Now, to get the qn, we want to modify this so that every part is distinct. Every part is distinct. That means that each I occurs 0 or 1 times. So each I in the partition, each integer I, either doesn't occur or it occurs at most once. So in order to modify this product, to get rid of situations where we have an I occurring more than once, we can just cross out the terms that correspond to having more than one I. More than one I is like 2i, 3i, 4i, 5i, and so on. So we just get rid of that, get rid of that, get rid of that, and just keep it going forever like that. And this is no longer the product of the PI, so got to get rid of that because the equation is no longer true. But this is what we're looking for here. So we just get rid of any of the terms corresponding to having more than one I. And so here is the product of polynomials to give us our generating function for the Q. Let me actually erase a bit. Okay. So Q of n is the number of partitions of n in which every part is distinct, and K of n will be the number of partitions of n in which every part is odd. So again, we're trying to show that the number of partitions of n in which every part is distinct is equal to the number of partitions of n in which every part is odd. So we're going to try to show, what we want to show is that Q of n equals K of n for all n. So that's the goal. And we already have the generating function for the Q of n. So we can represent it as this product. And we'll try to manipulate that product in order to get something that's equivalent to a generating function for K of n. So there's the product that we got for the generating function for Q of n. So it's the same thing we got at the top, but written more legibly, is the product I equals 1 to infinity of 1 plus x to the I. And this is the same thing as the generating function for Q, which is sum n equals 0 to infinity of Q of n times x to the n. So we can see how this compares to our standard generating function, the standard one, n equals 0 to infinity. And we call this one P of x. Take P of x, Pn x to the n, and this was this product I equals 1 to infinity of 1 over 1 minus x to the I. So for this one right here, we don't have 1 over anything. We just have 1 plus x to the I. So no denominators. And here's a way that we can write it in a slightly different form. And this is going to be helpful for manipulating it into the generating function for K of n. So we started with this right here, the product I equals 1 to infinity of 1 plus x to the I. Now we can take each term in that product and just multiply it by 1. And again, I'll mention my assumption, absolute value of x is less than 1. So we don't have any issue here with dividing by 0. So we multiply this by 1, and 1 is in the form 1 minus x to the I divided by 1 minus x to the I. So we multiply by 1 minus x to the I over 1 minus x to the I. We do that to each term, the 1 plus x to the i's. And we can write that just as the product I equals 1 to infinity of 1 minus x to the 2i over 1 minus x to the I. And we can write this out. So let's take that product that we have right here. And I'll write it down here, I guess. So we have 1 minus x squared over 1 minus x to the 1. 1 minus x to the 4th over 1 minus x squared. Let me just keep it going. I'm just going to write out a few terms of this just so we can see why we have this mass cancellation. Okay, this is the last one. I won't do any more after that. Okay, dot, dot, dot. So this big product here. And then we start canceling things. 1 minus x squared cancels here. 1 minus x to the 4th cancels here. 1 minus x to the 6th cancels here. 1 minus x to the 8th cancels here. The next one would be like a 1 minus x to the 8th. 1 minus x to the 16th. It just keeps on going, dot, 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 forever. So all the things in the numerator get canceled out. And they cancel out with the even powers in the denominator. And so what are we left with? We're only left with the, so we're left with the odd powers in the denominator. And only the odd powers. All the even ones get canceled. And here are the odd powers. So we have 1 minus x to the 2 times 0 plus 1. So we can write this one here, this product, bring it over here. So we have 1 over 1 minus x times 1 over 1 minus x to the 2 times 1 plus 1, so x cubed, times 1 over 1 minus x to the 5th, and so on. And that's exactly what this product was, where we cancel all that stuff out. So that's what we get when we cancel things out. We get the product j equals 0 to infinity of 1 over 1 minus x to the 2j plus 1. Now I should erase a little for our next bullet. So here we go. So now we just want to see this product that we got. Can we somehow show that that product is the generating function for k of n, where again k of n was the number of partitions of n in which every part is odd? So we can look again at our standard partition function. So our standard partition function was the product I equals 1 to infinity of pi of x, which was for each polynomial pi, it gave us the contribution of the i's. So having i's in the partition. So we wrote this out. I equals 1 to infinity of 1 over 1 minus x to the I. So if we only want to have odd parts, so we only want the terms in the sum to be odd. So to have only odd parts, we can just restrict I to odd values. So this product allows I to take on any value. If we only want I to take on odd values, so if we want to get the sum n equals 0 to infinity of k of n times x to the n. So this is our generating function for k, the number of partitions of n in which every part is odd. We can just write this as the same product I equals 1 to infinity of pi of x, except we need the extra restriction that I is odd. So we only include the I values for which I is odd. Another way to write this is as the product 1 over 1 minus x times 1 over 1 minus x cubed times 1 over 1 minus x to the 5th, and so on. So this is p1 of x, p3 of x, p5 of x, and so on. And so we see that this is exactly what we got in this bullet. So the generating function for k is the exact same as the generating function for q. And so now I should erase some of this so we can see the last bullet. I might just clear it all. I'll save it though. Okay. So that's our generating function for k that we just got. So we can write it as the product j equals 0 to infinity of 1 over 1 minus x to the 2j plus 1. In other words, this right here is the exact same product we got right up here. So these are equal to each other. And that means that we showed that the generating function for k of n is the exact same as the generating function for q of n. In other words, the sum n equals 0 to infinity of k of n times x to the n is equal to the sum n equals 0 to infinity of q of n times x to the n. That means that q of n has to equal k of n for all values of n, including 0. So we just proved the claim. That's how we proved it. We just showed that the number of partitions of n in which every part is distinct. Oops, sorry. So the number of partitions of n in which every part is distinct is equal to the number of partitions of n in which every part is odd. And here's a problem for you to think about. This problem is very simple. similar to the last one. So it looks like a similar sort of claim. And the goal here is to prove or disprove. So the claim looks similar, but I'm not saying whether it's necessarily true or not. So see if you can prove or disprove that the number of partitions of n in which every part has at most 2 occurrences. In other words, every term in the sum occurs at most twice. And the claim, which might be true or false, because I said, again, prove or disprove. So the claim that you need to prove or disprove is that this set of partitions, the partitions of n in which every part has at most 2 occurrences, has the same size as the set of partitions in which all parts are not divisible by 3. So let's look at an example just to illustrate this one, just for clarity. So the standard example we've been looking at, n equals 5. So we have our 7 partitions. So that should be all of them. Now, partitions of n in which every part has at most 2 occurrences. So this one has a part with 5 occurrences. It's not at most 2. This one has every part with the most 2, because we have one part with 1, one part with 2 occurrences. This one has a part with 3, so that's not good. This one has a part with 2, a part with 1. That's fine. This one's fine. Each part has at most 1 occurrence, at most 1 occurrence, 1 occurrence. So these, all of the ones with checks are fine. So I guess I'll do the count for the checks right now. For the ones on the left, it looks like we have 1, 2, 3, 4, 5. Okay, now we can count the partitions in which all parts are not divisible by 3. All the parts here are 1, so all parts not divisible by 3. Here we have a part equal to 3, so nope. All the parts here are less than 3, so none of them are divisible by 3. Same here, everything less than 3, nothing divisible by 3. Here we have 2 parts, neither divisible by 3, so that's good. Here we have a part equal to 3, so that would not work because it has a part divisible by 3. 5 is not divisible by 3, so that one works fine. So we get a total of 5 there. So it seems like it matches up at n equals 5. So see if you can either find a small counterexample or see if you can prove it somehow, possibly using generating functions. And I think that brings us to the end of the video. So thanks for watching.